My name is Grover Welch, and in this video I'll be demonstrating how to run a one-way analysis of covariance, or Ancova, using SPSS. The dataset I'm working with contains math test scores for 90 students across 3 classes taught by teachers named Smith, Jones, and Brown, along with the number of classes periods each student missed, which serves as our covariate. The research question for this assignment is there a statistically significant difference in math test scores between classes after controlling for the number of periods they missed? The null hypothesis states that there is no significant difference in test scores between classes after controlling for periods missed. The alternative hypothesis states that there is a statistically significant difference in test scores between classes after controlling for periods missed. And before interpreting my Ancova, I need to verify 2 key assumptions: homogeneity of regression slopes and homogeneity of variance. To check the first assumption, homogeneity of regression slopes, I need to run a custom model that includes an interaction term between the factor, class, and the covariate PMissed. So I'm going to click. So what I did was I clicked Analyze, and I went down to General Linear Model, Univariate. In the univariate dialog, I moved test to my dependent variable, class to my fixed factor, and periods missed to my covariate right there. And then I moved, then I clicked on model, and I want to switch to build custom terms. So I went to build custom terms. I clicked, I added class first by doing this right here and then hitting add. Then I put it right here and then put periods missed the same way. And then I decided to highlight both class and period missed at the same time. So I confirmed that interaction is type drop down and clicked add to create the class by periods missed interaction term. Then I click continue. I've already run this data, so. All right. In the output, I'm looking at 2 things. I'm going to look at the Levene's test and the test of, so under the options, I also checked homogeneity test, and then I click continue and OK. And in the output, I'm looking at 2 things: the Levene's test and the test between subjects effect table. So my Levene's test one is right here, and then followed by my test of between subjects effects. All right, my Levene's test for the interaction model gives me a F of 2, a DF of 2 and DF of 87. MS, where am I at? My F of 2 and 87 equals a 0.754 significance. And because the P is greater than 0.05, the variances are equal across groups. For the interaction term, class by periods missed, the P value was 0.488 right here. Because that was greater than 0.05, the interaction is not significant, and that confirms that the relationship between periods missed and test scores is consistent across all 3 classes. And so the assumption of my homogeneity of regression slopes is met, and we can proceed with the standard Ancova. Now the main Ancova will also run a Levene's test, and then we'll look at that output, and we see that 2.2 and 87 equals 0.371 and P equals 0.691, and that is also non-significant, which confirmed our error variances. With both assumptions confirmed, we're clear to interpret the full Ancova. So to run the full Ancova, I went back to Analyze. Now I went to General Linear Model. I went to Univariate. The variables stayed the same. I clicked on Model, and this time I wanted to go full factorial, so I hit full factorial. Then I hit Continue. All right. And then under EM means, I move class to the display right here, and I check for compare main effects, and I change my confidence interval to Bonferroni, and I hit continue. Again, I have already run this data, so I'm using the same data output. All right, so here in my data output, here's my descriptive statistics right here. So Smith had a mean of 84.10, and that's the highest raw average of 84.10, and while Jones' class is the lowest at 79.93, and Brown's class sit kind of in the middle with 80.47. Then I go down to my test between subjects and effects, and after controlling for periods missed, the main effect of class is statistically significant. So the F of 286 right here, and that equals 4.116. My F statistic of 4.116 with a significance of 0.20. And because 0.20 is less than 0.05, I reject my null hypothesis. There is a significant difference in math test scores between classes. Now, the partial eta square value is 0.087, indicating a medium effect size. So class membership accounts for approximately 8.7% of the variance in the test scores after accounting for attendance. So the differences are not only statistically significant, they are practically meaningful. The covariate periods missed was not a significant predictor for test scores in this sample. F1 of 86 over 86 equal to 0.001. And a P of 0.969 with a partial eta square of essentially 0 right here on this side, periods missed. All right. Estimated marginal means represent each class's adjusted test score after statistically controlling for periods missed, and they're evaluated at the grand mean of the covariate, which was 3.43 periods. There we go. Right here. After controlling for periods missed, Smith's class has the highest adjusted mean at 84.10. That's followed by Brown's class at 80.47 and Jones's class of 79.93. These adjusted means are very close to the raw means because periods missed was not a significant predictor in our data set. Pairwise comparisons, Bonferroni corrected. Since the overall test was significant, I now look at the pairwise comparisons to determine which specific classes differ from one another. And these Bonferroni corrections to control for multiple comparisons. So looking at Smith versus Jones, we have a mean difference of 4.165, standard error 1.575 with a P of 0.029. That's significant. Smith is greater than Jones. So looking at Smith versus Jones, the difference is 4.165 points, and the Bonferroni corrected P value is 0.029. Since 0.029 is less than 0.05, this is statistically significant difference. Smith's class score is meaningfully higher than Jones's class after controlling for attendance. Smith versus Brown has a p-value of 0.075, which is just above 0.05. So that difference is not statistically significant. And Jones versus Brown gives a p-value of 1. Essentially no difference between these two classes. APA conclusion: a one-way analysis of covariance was conducted to examine whether math test scores differed between three classes, Smith, Jones, and Brown. After controlling for the number of periods missed, preliminary assumption testing confirmed that the homogeneity of regression slopes assumption was met, as the class times periods missed interaction was not significant. F2 and 84 equaled 0.723 with a P of equal to 0.488. Levene's test confirmed equality of error variances with an F of 2 and 87 was equal to 0.371. P significance equals 0.691. After controlling for periods missed, there was a statistically significant effect of class on math test scores. F2 of 86 equals 4.116. P significance equals 0.020 with an eta squared of 0.087. The covariate periods missed was not significantly related to test scores, with an F of 1 to 86, which equaled a 0.00, with a P equal to 0.969. So the estimated marginal means indicated that Smith's class adjusted M of 84.10 scored significantly higher than Jones's class adjusted M of 79.93, P of 0.029. The differences between Smith and Brown, P equals 0.075, and between Jones and Brown, P equals 1, were not statistically significant. In terms of meaningfulness, a partial eta square of 0.087 reflects a medium effect size, so class membership accounts for approximately 8.7% of the variance in test scores even after accounting for attendance, which suggests that instructional differences between teachers have a real practical impact on student performance. The null hypothesis is rejected. There is a statistically significant and practically meaningful difference in the scores between classes after controlling for periods missed, and the difference is specifically driven by Smith's class outperforming Jones's class. Thank you for watching.